Share screen. All right. Questions? I can't promise that we don't have quizzes. So let's see. All right, so let's start, and I'm gonna start with this table as usual. Okay. Okay, so this is our table. Our axes, x, y, z, linear velocity. Oopsies. Okay. Anyway, axes, our velocity components, forces, and these large x, y, and z, as we discussed last time, they are simply aerodynamic and propulsion forces. So there is still, the gravity is not included here. These are not all the forces. We just simply need to add gravity. The angular velocities, like these are the components of the angular velocity vector omega. The moments, LMN, roll, pitch, yaw. And based on these definitions, we simply derived the equations of motion. Force equal mass times acceleration last time. These were the things. So here is mass times acceleration. Mass times acceleration here. That's good. This is equal the forces. So I'm gonna do here. This is equal to the forces, and like I said, the forces were two types of forces, x, y, and z, aero and propulsion, plus gravity, which is unknown as a components in the body axes. Like it's known as magnitude, mg, right? We're gonna talk about this in a minute. Actually, this is the topic of today. So, and also we have the moment equations. So 3 equations for the forces, translational motion, and 3 equations for the moment, rotational version. So if I want to draw a block diagram here, maybe this is good. This is rigid body dynamics, which is applicable to airplanes, spacecraft, submarines, cars, whatever you like. In a typical dynamics problem, we're given the forces, Fx, Fy, Fz, so the total forces, like the XYZ plus the gravity. And we're also given the moments, Lmn. We're given the applied loads. And it is required to determine the motion, so UVW, PQR, and indeed these 6 equations in 6 unknowns. The unknowns are the motion, UVW, velocities, and PQR, angular velocities. These are the unknowns from these 6 equations, and the 6 quantities that we need to know are the forces and moments. And again, this is applicable to any rigid body you like to analyze. Any questions so far? So this is what we did last time. And this is the very beginning of part 2, which may be the very beginning of the entire course, like we discussed last time. Any question about this? All right, so in order to solve for the unknowns, I need to know the applied loads, like any dynamics problem. And last time we discussed that the source of these will be coming from aerodynamic model. Aerodynamic forces and moments, aerodynamic loads coming from an aerodynamic model, which we will have next lecture. Okay, so assume that someone is magically giving you the aerodynamic forces and moments, large X, Y, Z, L, M, N. Are you ready to solve the equations of motion? Actually, no, because we still need to completely know the F of gravity. Well, what's the issue with it with F of gravity? We know that it's just mg straight downward. What's the issue? The issue is as follows: is that when the airplane has some attitude like this, what happened? So this is the body axis, X body, Z body. But the inertial axes, this is X inertial and Z inertial. Inertial means fixed or moving with constant speed, so there is no acceleration. So usually we take it fixed. So these are inertial axes. The body is usually inclined. So I have these kind of angles. This is the pitching angle of the body, theta. This is the angle, theta. So if I have the gravity here straight downward, mg, in this case, I can simply do cosine and sine to get the gravity component along the X body and Z body and so and so. But this is not the only rotation, right? As you guys know, we can have something like so again, this is the Z body because it rotates with the body. This is Y body, the body axes that are attached to the body, and the inertial axes, they're fixed, they don't rotate. This is Y inertial, this is Z inertial, and this angle is the roll angle of the body, what we're gonna denote by phi, the roll angle. Again, gravity is straight downward, mg, and I can do cosine and sine, that's fine. So if I have a single rotation, I can simply do cosine and sine, but if I have them both simultaneously, along with the third, so I have 3 rotations in general, roll, yaw, and pitch, how can I get the gravity component along the X and Y and Z body? Okay, so this is the objective of today. What is this guy? I know the magnitude of it, it's mg, but the components along X, Y, and Z, this will depend on the orientation of the airplane. So I need to determine this in general for a general orientation. Any question about the objective? Any questions? Yep.
Could you just go over what the objective is again? Just,
yeah. So let's see. So we're gonna do we're gonna do it generic. What is the objective in general? Is to relate the body frame X, Y, Z body to the inertial frame, so that if I have any vector in one of the 2 frames, I can get it in the other frame. In particular, what I really need here to complete the equations of motion is the gravity. I know the gravity in the inertial frame. What is the gravity in the inertial frame? What are the components of the gravity in the inertial frame? Well, there is, it's straight downward. So it's 0 in X, 0 in Y, and mg in Z. So I know indeed the gravity as a vector in the inertial frame. I know the component. It's 0, 0, mg. Well, I need these components in the body frame because this equation of motion is written in the body frame. So I need to relate in general now. This is the objective as a generic objective so that you can apply to airplane flight mechanics or anything else. I mean, this is a very useful tool, is to how to relate the body frame, a rotating frame, to an inertial or fixed frame, so that when you have something in one of the two frames, you can immediately get it in the other if you like. Okay, so this is the objective. So anything above this black line is the motivation from our course. Anything down this line is generic and actually new, in the sense, you know, we did not discuss it before at all. This chunk starting from here to the rest of the lecture, you can actually cut it and paste it in many courses. In particular, I cut it as is, exactly as is, and paste it in my 241 graduate dynamics. I'm saying this because I'm also like to stress that it almost has nothing to do from before. So you can start fresh, even if you did not. We know already that part 2 has almost nothing to do with part 1, but we had only one lecture in part 2, and even this lecture, we don't need anything from it. This, we just need the lecture to know this story, but the tool itself, starting from here, is completely new. And the objective is to relate some rotating frame to a fixed frame. Any question about that? Any question about anything below the black line, which is simply the objective now? Okay, so let's do that. Let's do that. How can I do that? So, seems some questions here. Homework 5, I'll post it right after the lecture. It's 2 problems about today's lecture, so it should be fine to do it in 3 days, Wednesday, Thursday, and Friday. All right. So let's get this thing and put it here. So this is a given attitude. I have an airplane or any rigid body. A given attitude. Someone is giving me this picture, right? So this picture, this is X body, right? And this is along the span of the wing. This is Y body. It's not vertical. Okay, it's 3-dimensional. And this is Z body, right? These are the axes of the body that rotate with the body. And I'm given this attitude, I'm given this picture. I don't know how the body arrived at this attitude. So initially, at the beginning, we assume that the two frames are aligned with each other. So the body frame is aligned with the inertial frame at the beginning. So theta is 0, phi 0, all these angles are zeros, okay? And then the body did some excursion, some maneuver to arrive at this given attitude. And I really don't know what the body did in the middle to arrive at this attitude. All what I'm given is this final attitude. And I don't care about what happened in the middle. All what I care about is how to relate this final attitude, final frame, to the inertial frame, okay? This is my objective. I'm given a frame, and I need to relate this frame to the very old one, the inertial frame that did not rotate, okay? To do this, I mean, there are several ways, but Euler has actually a very good hypothesis that is very useful. He stated the following, that the attitude, or any, stress the word any, attitude, any frame of a rigid body can be represented by at most, and again I'm stressing at most, so 3 consecutive rotation. So Euler is suggesting you a way, hypothetical way, to arrive at this final attitude, final XYZ. You start with the inertial one and do 3 consecutive rotations. Do any 3 rotations about 3 independent axes. And he guarantees you that with some angles, you will arrive at the given attitude. So you can relate the 2 frames together. This is the objective today. I mean, we're gonna go through this in detail. So what do you mean? So we have at the beginning, we start with the inertial axis, XYZ inertial. And Euler is asking you, okay, do any 3 consecutive rotations. Maybe you can rotate about Z inertial, to arrive at a new set of axes, right? And then rotate about one of these new axes, maybe the Y among them, to arrive at another, this is now 3rd set of axes, right? We have the set at the beginning, we did another 1 rotation about Z, very first Z. And then we did another rotation about the intermediate Y. We arrived at the 3rd set. We're gonna do a 3rd rotation, say about the most recent X. These are 3 consecutive rotations. Euler guarantees you, if you do this with some angles, you're guaranteed to describe this given attitude. And we will see how we do that, okay? But let's discuss the following. What do you mean about that? Let me because there are many possibilities here. I can really rotate first time about Z, or I can rotate about Y, I can rotate about X. And when you do first rotation about Z, the second rotation you can do about Y or X. And the 3rd rotation you can do about X or about Z. So we can have something like Z, Y, Z. How this is possible? Because remember, this Z is very different from that first Z, right? We have a set of axes at the beginning, X, Y, Z. We rotated about Z. We arrived at new X, Y, Z. The Z remains fixed. This Z remains fixed because we're rotating about it. So I arrive at new XY. In particular, I'm rotating about this new Y. When you rotate about this new Y, Y remains fixed because you rotate about it. But X and Z change. So this Z is different from the very first Z. Any question about that?
In what ways is it different?
Is a different axis. So maybe the first Z is like this. This last Z is definitely different. It's not the same axis. It's somewhere else because I rotated already.
I see.
I rotated.
But would it still be in the same area on the airplane?
The same area?
Because, for instance, the same point, because the airplane would be rotating. So would it just go along with the airplane?
All of these are located at the same point, but we just rotate. We don't translate. Okay. So
Okay.
simply rotate, and so the origin remains fixed. That's a good question. So let me tell you the following. Assume that I rotated about, so I have XYZ inertial. So XYZ inertial, so X is forward, X inertial, Y is to the right, and Z inertial is straight downward. Okay. And I made rotation about this Z inertial by 30 degrees. Okay, so I arrived at new XY because the new Z is the same as the old Z. I just rotated about it. Okay, it remains fixed. Okay. So I rotated about this Z inertial by 30 degrees. Can I do the second rotation about this Z again? The answer is no, because this is not a new rotation. If you do the second rotation by 20 degrees, it's as if you have only one rotation about Z by 50 degrees. So this is not a new or independent rotation. Okay? Any question about that? So let me give you, to show this, I'm gonna stop sharing here for a while, and I'm gonna maybe open my video to show you something. If we are in person, I would bring this to the class, but hopefully you can see. So let me show you, assume that I'm given this attitude. So here is the beginning, here is the beginning. So at the beginning, the airplane is aligned with the inertial axis. So it's a straight and level flight. Everything is fine. The Z of the airplane, Z body, is straight downward, aligned with Z inertial. Everything is fine. All the angles are zeros. And here is the attitude that I'm given to represent. It's as if the airplane yaw 90 degrees. This is the given attitude, okay? This is the given one. Yaw 90 degrees. So I'm given this, and I don't know how the airplane arrived at this attitude. And I want to represent it. Okay, we have many possibilities. One obvious possibility is we assume that the airplane yawed 90 degrees to arrive at this given attitude. Here is another possibility that might not be obvious. I'm going to roll 90 degrees. I'm going to pitch 90 degrees. I'm going to roll back negative 90 degrees. The final result is exactly the same. So this given attitude, I could have easily represented by two possible ways that we can simply visualize. One of them was yaw 90 degrees, simply rotation one, rotation about Z. The other possibility was rotation about X, roll. Rotation about Y, the most recent Y, because remember, my Y now is downward, right? Once you roll 90 degrees, your Y is downward. I'm rotating about Y. Here is about Y, the most recent Y. And now I'm rotating about X again, negative 90 degrees. 3 rotations about what? X, Y, X, okay? But the last X is different from the very first X. Where is the very first X? Is towards you, right? Once I rotate 90 degrees, what is my X now? It's still towards you because I rotated about X, it remains the same. Now, when I pitch 90 degrees, what is my X? My X is this way, is not towards you anymore, right? So now if you rotate about this last X, you arrive at the yaw 90 degrees. I hope this is clear enough, or at least give you a visualization. I mean, you don't have to stick to this example. At least all what I want you to get out of this is that given a final attitude, there are many possible ways to arrive at this final attitude. There are many possible rotation sequences that if you follow, you can arrive at the final attitude. Any question about that?
I just had one. So
Yes,
if it's like a X, Y, X or like Y, Z, Y, are you always going to rotate the opposite of the first rotation?
No, not necessarily. No, not necessarily. Here was, here because we rotate just to match the final attitude. This is the goal. Okay.
Professor?
Right. Yes, Ethan?
So just a question. So like for the work that we're about to develop then, like, so what we're doing is like, we have a final like orientate the attitude and multiple different paths that we could take to get there.
Exactly, exactly.
Are we is the work that we're doing basically gonna be like tracking the different like paths?
Yes, we're gonna hypothesize, we're gonna assume, because we really don't know how the body arrived at this final attitude, right? So we're gonna hypothesize or represent this final attitude by 3 rotations in the middle. So they are fictitious rotation. The body really did not do this, but this will be very useful for us to represent this final attitude. Okay. Yes, we're gonna track this intermediate rotations, the 3 intermediate rotations to arrive at the final one. Okay.
Okay. Thank you.
Mm-hmm. Any more questions? All right, so let me share again and go back here and continue with our possibilities, because we said one obvious possibility at the beginning is to rotate about Z, the most recent Y, and then the most recent X. Okay, we're done. Then we said, no, we can do actually Z and Y and then Z again, because this final Z is different from the very former Z. Okay. And I can change Y at the beginning. I can keep Z fixed. I can change Y at the middle, I'm sorry. So I can here say Z and then rotate about X. Then it also gives me two possibilities. Rotate about Y or Z, X, Z, right? Any question about that? So you can see if I start with Z at the beginning, I got actually 4 possible combinations. And no one ever forced me to start rotating about Z. I can start rotating about Y, getting different 4 possible combinations, or I can start rotating about X, getting other 4 possible rotations. So in total, there are 12 possible combinations. Okay? There are 12 possible combinations where you can represent the attitude, the final attitude of a rigid body. This is the standard one. You'll find it in many books in airplane flight mechanics and spacecraft attitude dynamics. This is the standard one. We call it yaw because we rotate about Z at the beginning. This is yaw motion, right? And then pitch because it's about Y, and then roll. This is the standard name of it, yaw, pitch, roll. Or some books call it ZYX sequence. So any of these, we call it an Euler angle sequence. So the very first one is the standard one, and we're gonna derive it in detail in this course, but you are required to derive any of them. Actually, you will find in the homework and in the final, derive one of these non-standard things, because it tells us how deeply you understand things. And you're free to use the standard one without derivation. We're gonna derive it in detail together now. Okay, so this is what is its standard name. It's yaw, pitch, roll, or ZYX, or sometimes 3, 2, 1. Why? Because usually the numbering of the axes are XYZ, 1, 2, 3, right? Here we start rotation about the third axis, then the second axis, then the first axis. So for example, the second combination is, we call it 3, 2, 3, okay? Sequence, and so and so. So let's see now how this rotation, let's pick one and try to see how we do it. Like, what we keep now discussing things and they are not tangible. Let's see how we do this. It's actually super easy. So what's the objective? The objective is that I'm gonna start with the inertial frame, and I wanna hopefully arrive at the end at the body frame, right? And Euler is telling me is that you can link these two by 3 consecutive rotations. Any of this will work. In particular, we're following the purple one, the standard one. So let's do it. So from at the beginning, I have XYZ inertial. I'm gonna do 1 rotation at a time. So I'm gonna rotate about Z inertial, right? By an angle psi. I'm gonna call it psi, okay? To arrive at a new frame, XYZ. Let's give it a name. I'm gonna give it a name E frame. So I started with XYZ sub I inertial. I rotated about Z inertial. So it remains fixed because I'm rotating about it, but X and Y change. In the new frame, I have XYZ subscript E, okay? X and Y are new because they are rotated, and Z remains the same. Any question about that? So, and now from E, I'm gonna do the second rotation suggested by Euler, which is about the most recent Y, which is YE, right? By some other angle. It's called theta, your pitching angle, theta, okay? To arrive at a new frame, let's give it a name, say the S frame. Okay? And finally, this is rotation about what? Can you tell me? So I'm following this thing. X. What X?
X.
Exactly. It's the most recent. Always I'm rotating about the most recent. So this is XS by some angle. We're going to call it phi. These angles, psi, theta, phi, are what we call Euler angles. So you're going to make here a new columns. And say Euler angles. The roll angle, we call it phi. The pitching angle, we call it theta. The yaw angle, we call it psi. Okay? This diagram, this color diagram that I just did, it's simple, but it is the basis for all the derivation I'm going to do today. I'm going to do two main derivations today, and you're required to do any of them for any of the non-standard sequences. Okay? So you really need to get this. And because I deem this as very important, I will ask about it whenever I have a chance, in final, in homework, and whatever. So you really need to get this. And like I'm saying, this is the very beginning. This is the basis. Once you get this right, everything will follow off naturally. So let me see if you have any question about this diagram. So for example, if I tell you, please do ZXZ, or the 3-1-3 sequence. Well, this will be rotation about Z. This will be rotation about what? About X. Okay? And then the final will be rotation about Z. Okay? Any question?
Yeah, I have a question real quick.
Yep.
So yeah, if you do the ZXZ, are we keeping the angles attached to the rotation? So like the first one for the Z, like we know that it would be psi. But the
naming, the name, that's a good question. The naming of the angle is this is by convention. Yeah, like it's arbitrary. We can call it actually alpha, beta, gamma angles. Okay. Yeah, the name just.
So the second Z would be attached to the last angle still.
Yeah.
Okay.
Yeah, that's an important point. Yes. All right. Any question about any more question about this diagram? It's very important. Because the rest is super easy. What I'm going to do the rest, I'm going to take one rotation at a time. And one rotation happening in the plane is super easy to follow. This diagram is super important. So let's do the first rotation. Yes.
What does the S stand for again?
No, these are fictitious names, right? I call this E frame. Okay. Remember, we're only given the final attitude, right? I really don't know if the body did this or not. I'm just assuming that, okay, let's assume that to reach this green final attitude, the body did 3 rotations. So from the inertial frame, which is a physical frame, okay, it arrived at the intermediate fictitious frame in the middle called E. And another intermediate fictitious frame in the middle, I just called it S. You call it whatever you like. But then I arrived at the final frame, which is the body frame. Again, it's a physical frame. So indeed, the two frames that can be visualized and they have physical meaning in this diagram is the very first one, the inertial, and the very last one, the body. The intermediate ones are fictitious. They are just helping me to relate the two very far frames from each other. Okay. More questions? Let's do the first rotation to see how easy it is. So simply I have, this is about Z, so it's happening in the XY. So this is X inertial, Y inertial, and I'm rotating by an angle of psi to the blue frame. So this is XE, YE. The angle is named psi. I mean, you can call them whatever you like. The standard naming are psi, theta, phi. All right, and now all what I need to do is simply relate the blues to the blacks. That's easy. So I need X, E, Y, E, Z, E. I need to relate them to the blacks. Fine. So let's do XE. What's the relation between XE and XI? Well, it's cosine psi. So this is actually cosine psi times X inertial. And if it's cosine here, it's going to be sine, of course, over sine psi times Y inertial. Any question about that? Any question about the first line? So let's do the second, YE. Here is YE. What's its relation with Y inertial? It's actually cosine. So this is cosine. I mean, and again, if this one is sine, the other one will be cosine for sure. And the same here, if this is cosine, the other one will be sine for sure. But you need to adjust your positives and negatives. So the relation between YI and YE, they are in the same direction. So this is positive, but YI and YE and XI, they are opposite each other. So this is negative. Any question about the second line? Any question about the second line? It's just simple component by component kind of thing. And the super easy relation between Z and E, the new Z and the old Z. Well, the rotation happened about Z, so it remains fixed. So actually they are exactly equal. Any question about that? So any question about these three? I'm done, right? I managed to relate XYZ new, the sub E, to the XYZ old, sub I. I'm done. All what I'm gonna do, just to make it nicer, I will just collect it in a matrix form. So I will do the following. I will say X, Y, Z in the inertial frame is equal to some matrix times X, Y, Z in the inertial frame, or sometimes we like to do like this, superscript. Do whatever you like. This is blue. Let's stick to the colors. Let's fill the matrix together from these equations. That's easy. Anything multiplied xi will go here. So this is cosine psi. Because we're going to have too many cosines and sines, I will use C for cosine and S for sine. And then whatever multiplying Y inertial, it's here, sine psi. And whatever multiplying Z inertial goes in the third element. There is nothing multiplying Z inertial, so this is actually 0. And here is negative sine, cosine, and 0. And the last one, there is nothing multiplying X, nothing multiplying Y, and there is 1 multiplying Z. So we're done. All right. Let's see. Yeah, that's fine. So here, simply I need XE, the blue one, from XI and YI. I mean, it's always the cosine, the angle in between. If the angle in between is cosine, the angle, and it's positive if they are in the same direction, negative if they are in the opposite direction. So XE, it has cosine psi times XI. Now, the angle in between is not psi, is the complement. So it becomes sine now, right? So sine psi times Y inertial. This is the first line. And again, XE is in the same direction as XI, and it's in the same direction as YI, right? Now, what about YE, the second line? Let's see, there's a question here. All right, and so yeah, it just the second one follows off. Okay, so this is actually, I managed to relate the blue to the black through just a linear relation. It's a matrix multiplication. This matrix, we call it a rotation matrix. And any rotation matrix is an orthogonal matrix. So the determinant is +1, and the inverse is simply the transpose. So I'm going to give this I'm gonna denote it by R psi about Z. So what is this? Let's see how do I read it, because this is very important. It's a rotation matrix by an angle psi about the Z-axis. Okay, wouldn't you say what Z? Because we have too many Z's here lingering around. There is ZI, there is ZS, there is Z body, there are too many Z's. Actually, no, I will not say what Z, because interestingly, it really does not matter. It really does not matter. What do you mean? I mean that if you're going from here, from I to E, and you're rotating about this Z, this will be the rotation matrix. If you're going from E to S and you're rotating about Z, this will be exactly the same rotation matrix. So this is very useful. Why? Because if you're doing any non-standard rotation, when you do the rotation matrix here about Z, it's exactly the same rotation matrix in the last rotation about Z. What is different is simply the angle. Here, if the angles are, say, alpha, beta, gamma, so I will have this with the angle being alpha for the first one and angle being gamma for the third one. It does not, the rotation matrix does not matter where do you come from and where are you going to. So this is a very important point, an interesting point. So you construct the rotation matrix irrespective where you come from and where you're going to. Any question about that? Another thing, actually, now on, we derive this in detail, okay? The rotation matrix here, we derived it in detail from this diagram. I don't want you, of course I want you to, know how to do it one time in your life, but I don't want you to do it like this every time. There is just a quick way of doing it. So let's see how to do it. That's super easy. It really just depends on what axis you're rotating about. You're rotating about Z, the third axis. So here is the third column and third row. If I am rotating about Z by an angle gamma, for example, can you give me this rotation matrix? Yes, of course. Rotation about Z, so it's the third axis. So the element 3, 3 will be 1, 0, 0, 0, 0. And I'm going to put this block always cosine, sine, negative sine, cosine. And just use whatever the name of the angle. If it's gamma, then it's gamma. And this follows for anything. Like, what is the rotation matrix about X by an angle alpha? Yes, of course, you can go and do a diagram like this and derive it in detail. But here is a shorthand way for doing it. This is the first axis. So here is the element 1, 1, and it will be 1, 0, 0, 1, 0, 0. Cosine, sine, negative sine, cosine. Whatever the name of the angle, if it's alpha, just put alpha. We're done. Any question about this? Any question?
Professor, I'm still, I'm sure I'll be able to think through it a little bit, especially over the homework, but the up above where you drew the diagram and then wrote out the sine and cosine and stuff, we're dealing here with vectors in those additions?
No, these are not vectors. I mean, they can be vectors and they can be scalars, frankly speaking. So,
okay, so we would be adding up there the scalar length of our new x?
Yes, yeah.
Okay.
Yeah. Mm-hmm. I'm relating x, the XYZ, the new, to the XYZ old. This is the main objective here. So from this diagram.
Okay, that makes sense. Yeah.
And I'm now telling you a quick way of constructing your rotation matrix instead of just go and derive it. So here is a rotation matrix about Z. Here is any rotation matrix about X. So this is for any rotation matrix about X. It will always look like this. This is what I'm trying to stress.
Professor?
Yeah.
So earlier you mentioned that because these matrices are orthogonal, that the determinant's equal to 1.
Yep.
And, you kind of like, you went on a short tangent where you were showing that diagram above, like different combinations we could take. And you said something that made it sound like what's the benefit of having the determinant equal to 1?
No, it's not a benefit. That's a very good question. I'm just giving you here on a side its properties.
Oh, okay.
Any rotation matrix will have a determinant 1. The second property is quite beneficial. What is the second property? Is that the inverse is the transpose, because the inverse is a lengthy operation, right? You do too many things to get the inverse, whereas the transpose is super easy. Just flip every row by a column and that's it. So these are two properties of any rotation matrix. Okay, so let's construct together a rotation matrix about y by some angle beta. What's that? Well, it's y is the second axis, so here is the element 2, 2, the second column, second row, right? And then I'm gonna do my thing, cosine, sine, negative sine, cosine, whatever the name of the angle is beta, so I'm gonna do beta, 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 and I'm almost done. Any question about that? Any question? One thing to note here is that whenever, for this short-handed thing, if you want to derive it, of course, derive it and everything will go smoothly like we did here. If you want to just construct it like this, first hand, which I always do, frankly speaking, in my solutions to the problems. If you do the second axis, there is a sign. Like most of the things when we do the second, if you do determinant, for example, always the second element, seems that the second has some curse in it. Any question? So now I can construct a rotation matrix about any rotation matrix about z, any rotation matrix about x, any rotation matrix about y. In particular, I'm gonna get my nice diagram because it's very important. Get down. Get back to my objective, relating the green body frame to the black inertial frame. Okay, what is the role of the rotation matrix? The role of the rotation matrix is very important. It simply relates the two frames. Whenever you have a vector in the new frame, it's simply the rotation matrix times the vector in the old frame. That's it. Any vector, velocity, acceleration, force, angular velocity, in the new frame, the components is equal to the rotation matrix in the old frame. And we simply just got a way to construct our rotation matrix. So we're basically done. Let's do this. Let's write down these rotation matrices together. Well, we already constructed the first one before. It was R psi z, that was 0, 0, 1, 0, 0, cosine psi, sine psi, negative sine psi, and cosine psi, right? This one, R theta y, is 0, 1, 0, 0, 1, 0, cosine theta, sine theta, negative sine theta, cosine theta. But like I said, the second is always cursed, so this is really positive, this is negative. And then finally, R phi x is 1, 0, 0, 1, 0, 0, cosine, sine, negative sine, cosine, right? So we constructed our three rotation matrices. Now let's do this rigorously. I'm gonna start with x, y, z for my body. I'm gonna start with here. I know that the new is always equal to the rotation matrix times the old, like here. Here there was only one rotation from I to E. The E components, the new components after rotation, always equal the rotation matrix times the old, like this equation. I'm going to apply this equation over and over again, and we're done. So the B components, which I want, they are equal to the rotation matrix here. Right? The rotation matrix that I have here is R phi X, times X, Y, Z, E. Any question about this equation? Any question? And what is this R phi X? Here it is. This is equal to R phi X as is. Now this guy, the red guy, I'm sorry. Oh, you guys, you're not following. This is S, right? So the B is this rotation matrix times whatever before, which is the S frame. Now I'm going to replace the S with the rotation matrix times whatever before. So here is the rotation matrix. What is this rotation matrix? Can anyone say?
That'll be the rotation about Y by theta.
Exactly. I'm going to multiply X, Y, Z. This is in the E frame. And can anyone suggest what is the next step?
We do the same thing with the E frame and take the matrix about Z by psi.
Exactly. So I'm going to replace this thing with, so the XYZ in the E frame by the rotation matrix R psi Z times XYZ in the inertial frame. And look at that. We did it. We related the green frame to the black. And this thing, let me give it what color, maybe this. This is our total rotation matrix. Okay, and please, when you do it, I mean, after you become comfortable with it, you know that, you know, the relation from I to B is really the multiplication of the three rotation matrices. So you're gonna just multiply them together and to get your total rotation matrix, and you know how to construct each one individually, super easy. But please do it carefully like this, because sometimes you get the order incorrectly, okay? So you get R psi here and R phi there. So do it just one at a time, okay? Any question about that? So indeed, X, Y, Z in the body frame, any vector in the body frame is equal to this total rotation matrix multiplying by this same vector in the inertial frame. Any vector V, any vector can be velocity, acceleration, force, angular momentum, linear momentum, anything. For any vector V, the components in the body frame, the three components in the body frame, is equal to this total rotation matrix multiplying by that column V in the inertial frame to get that column in the body frame. Any question about that? In particular, there was one vector waiting for us. We did all this for it in this course. There was one vector we really know its components in the inertial frame and wanted its component in the body frame. And we did all this to get here. That vector was the gravity force, right? If gravity in the body frame, we did not know it. Now it's this rotation matrix times the F gravity in the inertial frame. What's F gravity in the inertial frame? Anybody knows?
0 mg.
Exactly. So this is in the inertial frame. Please multiply these three rotation matrices carefully. to get just one matrix, 3 by 3, full of numbers, full of, you know, phi, theta, and psi, cosines and sines, and all that. Multiply this by 00mg, you will get is mg because it's multiplying in everything. Negative sine theta, cosine theta, sine phi, cosine theta, cosine phi. This was the three things that were waiting for us. So I'm gonna take them as is, copy, and go up in the equations of motion, because this term was waiting, this F of gravity. Yeah, this F of gravity. Here, okay? Any question about this derivation of the total rotation matrix? It all follows naturally from this diagram. Because again, I'm really gonna give you one of the non-standard sequences. And you'll simply make your diagram simple, step by step, and derive your rotation matrix from it. Any question about that?
Professor, can
Yes.
you explain why so how we get mg, that final, I guess the gravity force, why it has components negative s theta, that's just after you multiply all the matrices together?
Oh yeah, after you multiply by the rotation matrix. Yes, exactly. Because remember, what is this rotation matrix, the total rotation matrix? It's the multiplication of these three individual rotation matrices. So they're gonna be full of theta, phi, and psi, and so on and so on. Okay. Any question? All right. So what do we have now? What do we have? Let's see. We have equations of motion. Let's copy this. Let's copy this again. So we're done with this, and so this is our first derivation that you have to know by heart. And here is mass times acceleration equal forces, and the forces are simply two types: x, y, z, coming from aerodynamic and propulsion, plus this guy, gravity, right? So this is the equation of motion. Simply mass times acceleration equal forces, and we have two types of forces. And we have the rotational analog of it. Here is the rotational analog. So angular acceleration, I times the angular acceleration equal the moment, Lmn. Okay. Now let's see our block. We had our block before. Let's draw it again, that's fine. So we have here rigid body dynamics. We're assuming that we're given the forces X, Y, Z. Hopefully next time we will see how to compute them from an aerodynamic model. But now let's assume that we're magically given these forces. Like any dynamics problem, we should be given the forces. And required, it's to get the motion. Velocities UVW, angular velocities PQR. So 6 unknowns, 6 equations. But look at this set of 6 equations. How many unknowns do you see? Let's count them together. We have UVW, right? Lingering here and there. So these are 3. We have PQR, also lingering here and there. So these are now 6. Today, we just added one more term in green due to gravity. Of course, we know M and G, but we don't know theta and phi. These change with the flight, right? These are variables like U, VW, and PQR. So we just added 2. So actually, and in general, if you want to make things general, so it's as if we today added 3 unknowns, theta, phi, and psi, the 3 Euler angles. So now we have 6 equations, but there are 9 variables. So we need to do something about this. Either these theta, phi, and psi are not new unknowns, they are really related to the old unknowns, which are velocities and the angular velocities, or if they are not directly related, please derive equations for them, how they evolve with time, theta, phi, and psi, how the angles evolve with time. What is the rate of change of the angle? This is the point. What is the rate of change of the angle theta, the pitching angle of the airplane? If I have a single rotation, where is that? Here. If I have a single rotation, theta dot is what? What's the rate of change of the angle? Any question? Any suggestion? So let's see, what are these?
Omega, right?
Yeah, exactly. It's the omega. It's the corresponding omega. Omega has 3 components, but x, y, and z. Here we're talking about y. So this is indeed q. So if I have a single rotation, then theta dot's q, phi dot the rate of change of the roll angle is the roll rate, simply. And psi dot, the rate of change of the yaw angle is the yaw rate, right? But as always, we don't have a single rotation. We have them combined. All right, so we just said that we have 6 equations in 9 unknowns. So we need 3 equations for the evolution of phi, theta, psi, the Euler angles. And they are nothing but the angular velocities. That's exactly right if we have a single rotation. If it's combined rotations, the 3 together as usual, then this becomes a little bit not trivial like this. And we need to derive this relation. So the 3 missing relations here are relation between rate of change of phi, theta, psi and PQR. Okay? They are supposed to be trivial relation like this, but they are not because they are combined rotations. Simply, they are about different axes. PQR are the components of the angular velocity vector in the body frame, like UVW are in the body frame. So these guys are in the body frame. These guys are not in the body frame. If you look at our nice diagram, which we follow, everything follows from it. Look at this theta, for example. This is very far from the body frame. Look at the psi. Psi is very far from the body frame, right? So we simply need to bring everything to one frame to compare them to each other, okay? So this is the second derivation, and you're required to also do it. What is the goal? The goal is to do a relation that looks like this, but it's not trivial. To relate rate of change of phi, theta, psi to PQR. That's easy, and again, it will follow from the same diagram. Let's copy this diagram again. Here. Let's do this. This is easy. What is your angular velocity vector? As a vector, it seems that this needs, just 1 second. Okay. Just needed the charger. Okay. So what is the angular velocity vector? At the end of the day, the good thing about this is that we assumed the way the body did it. So we have access to how, we have access to the whole excursion, the whole maneuver. It is nothing but what we see in this diagram, 3 rotations. So the angular velocity vector is actually psi dot and theta dot and phi dot, right? Psi dot, it's actually about z, so it's 0, 0 psi dot as a vector, right? Because we need to add vectors now. And this is in the inertial frame, correct? Any question about that? So this is the first rotation. I'm gonna add, I did not finish. One thing before moving on, I know that it's in the inertial frame. It was about what? It was about z inertial, but z inertial is the same as ze, because the rotation was about z, it remains intact. So I could write 0, 0 psi dot in the inertial frame, or I could write it in the E frame. It's the same vector actually, right? Any question about that? Whatever you like, whatever convenient to you, keep it. So we just have it in the back of our mind. It's either in the inertial or in the E. Questions about this? Then I'm gonna add the second rotation. Oops. The second rotation is simply about y, so it's 0 theta dot 0. And what frame? Well, it's the blue frame. Keeping colors is good really here. But again, ye is the same as ys. So if I like, if it's more convenient to me, I can just write this as s if I like. Can anyone tell me the last vector? What is this vector?
0, 0 theta dot in the B frame.
It's in the B frame, I agree. That's right. So I'm gonna say here is B frame. But the rotation,
phi dot, sorry.
Phi dot, exactly. And it's about x. So actually it goes in the x, right? Phi dot 0, 0. And guys, when I ask you to do a non-standard rotation, please pay attention to this, because if I ask you to do zyz and the last angle is phi or gamma, I don't care about the name, then it's gonna be what? 0, 0 something dot, right? Okay. Sometimes I usually see these mistakes. All right, so this is in what frame? This is in the S, or like you guys said, it's in the B. I mean, whatever you like. And again, as you really see, everything follows from this diagram. So this is, it's very important to have this diagram right. Any question about this line? That this is the total angular velocity vectors. It's simply the vector addition of the 3 rotations that I have.
Professor?
Yes.
So the one in red in the body reference frame, if that one we were doing like, if that was for Z, then it'll be 0, 0 psi dot.
Yes. What do you mean? What do you mean? 0, 0 and the angle dot. Yes. Yeah. Yeah. Very good. Yes. Yes, Brandon.
Thank you.
Questions? Okay, this is a vector in the B frame or S frame, whatever you like. This is in a different frame. This is in a third frame. I cannot add vectors in different frames. I need to bring them all to the same frame and do the addition there. Okay. How can I move one vector, I'm sorry, from one frame to another? How can I do that? Any idea?
Really quick, Professor. I had one question. So just
yes, Ethan.
Understanding this right. So we're looking at the vector omega. So like, let's just say the first term.
Okay.
That 0, 0 E with respect to the with respect to I is equal.
Okay.
Same vector with respect to E. Is that what you're saying? Or?
Yes, that's what I'm saying, and it's interesting, isn't it? So look at this. Look at this. Look at this. Let me do it here with this, the nice colors. So this is what? 0, 0 psi dot in the I. And 0, 0 psi dot. Let me just here is just to. So 0, 0 psi dot in the E, right? This is from one hand. I'm saying this is exactly equal to 0, 0 psi dot in the I. How come? Whereas I cannot say something in that frame equal to something in another frame. They must be related by what? They are related by what? They are related by what? Anybody knows? Suggests.
Rotation matrix.
Rotation matrix, and the rotation matrices are psi z, right? Are psi z. This one we constructed before. I mean, we can construct again together. It's super easy. 0, 0, 1, 0, 0, cosine psi, sine psi, negative sine psi, cosine psi. Let's do the multiplication together, please. So cosine times 0 is 0, sine times 0, and 0 times epsilon. So the first thing is 0. The second, something times 0, something times 0, and 0 times epsilon. We multiply row by a column, right? Then the third, 0 times 0, 0 times 0, and 1 times epsilon. They are indeed equal. Okay? Because the rotation matrix is, because here the rotation is about z and the rotation matrix is about z. When you multiply them together, you get the same thing. Okay? Any questions so far? Any question about these two lines? I just wrote two lines here. Our diagram, and from the diagram, I constructed my total angular velocity vector. The rest is easy because, okay, we said we're gonna transfer all these vectors to the same frame and do the addition, and we're done. What frame do you like? Well, we need to relate these guys to the PQR, and since PQR are in the body frame, so let's do everything in the body frame. All right, so this means that this omega, I'm gonna write everything in the body frame. So this is PQR in the body equals. This guy was already in the body frame already, so that's good. So this is phi dot 0, 0. Very good. Now, this thing was in the S frame. Well, it's in the S or the E. It's up to you. But come on, I mean, we want to go to the body. S is closer to the body, so we're going to consider it as part of the S frame. If I multiply by this rotation matrix, it would be unnecessary because I would get the same thing like I showed here. So I would consider it as part of the S frame because it's simply closer to the body. So here is 0 theta dot 0. This is in the S frame. This is in the S frame. And to transfer something from the S frame to the body frame, I need to multiply by what?
The rotation matrix about x of s by
Exactly.
phi.
So this is r phi x. Now the result after the multiplication will be in the body frame. So I'm good. Okay. Okay, finally, plus this guy, again, it's in the I or E. Here is I, here is E. The goal is to go to B, so I'm going to consider it as in the E frame because it's simply closer to the body. And please do it one at a time. So I'm here in the E. Here is the E in blue, 0, 0 epsilon dot in the E frame. First, I'm going to go from the E to the S. So I'm going to multiply by R theta Y. This result is in what frame? It's in the S frame. And then I'm going to multiply by R phi X. So the result now after this multiplication is in the D frame. Okay? You have this rotation matrix. Go and multiply, please. You have these two rotation matrices, multiply them together, get a matrix, and multiply by the column. At the end of the day, we have 3 columns. We're just going to add these 3 columns component by component. Here is the result. Any question about that? So let me actually just to make it to you in a good way. So PQR here is equal to this first thing, negative sine theta psi dot cosine theta sine phi psi. This is after the multiplication. Cosine theta cosine phi psi dot. Because the first element, the first term, all related to psi dot, plus the second, which was related to theta dot. This was 0 cosine phi theta dot and negative psi sine phi theta dot. The third will come as is, right? This guy was already in the body frame. So this is plus phi dot 0, 0. Simply add them component by component to get these equations that we were waiting for. We were waiting for equations that relate rate of change of Euler angles, dots of phi theta and psi to the PQR. Because now we're going to add these 3 equations to the 6 equations. We will have 9 by 9 equations. The 9 equations. What are the 9 equations? 3F equals MA translations. 3 equations of motion like F equals MA, but the rotation. And these last 3 kinematic equations, we call them rigid body kinematics. These are the 3 equations. These are the 9 equations. What about the 9 unknowns? UVW, linear velocities, PQR, angular velocities, and like I said today, we added phi theta psi, the Euler angles. Questions? Questions?